Hello, everybody.
It's MoNaCo, y'all.
And Milks.
Try and be loud for you. Had some people talking about we were a little bit faint.
Yeah. No faint here. Drink the caffeine, man.
Yeah.
Drink the caffeine.
Third homework video. First impressions of this last quarter and almost our last unit. Those of you got some people are really doing homework, and I'm digging it. At home.
Yes.
I mean, I got some kids who are already 30% done with the unit on day one.
I think the message that we need to get very clear is that now that we've given you guys some choice in class, that the choice isn't going to be that you can get everything done in class. If you're not doing stuff outside of class, guys, your chances of being very successful are slim.
Curtains.
Here we go.
6 and 7 are the pages of interest in this little lecture.
Yep.
We're going to learn what reduction and oxidation reactions are and how to assign our oxidation numbers. I'm not going to shout. That's about as loud as I can get. So pay attention.
Yeah, so what exactly is a redox equation, and how do we assign these oxidation numbers?
So let's start with some definitions.
Okay.
Oil. Oxidation is losing E negative. What's an E negative? An electron. So oxidation is all about losing electrons.
There you go. And when any atom in a reaction loses one or more electrons, it is being oxidized.
Right. Now the definition of a reduction is the gain of an electron. So naturally,
reduction is gaining
electrons. Mm-hmm. And so any atom in a reaction gains one or more electrons. It has been reduced.
Right.
Wait a minute. Reduced?
So you think about the oxidation state that it has. If I was a 0 and I gain an electron, I become a -1.
So I'm reducing my charge. That's where the nature of the word comes from.
It is. And unfortunately, again, it doesn't work that way for oxidation, but it does for 1. So if you can do it for 1, then you can reason and logic your way through the other
Come
one.
ask MoNaCo why oxidation is not called gaination.
Wait. The key part there is ask MoNaCo, not Milks, because I don't want to hear it.
2 memory devices. Oil rig. That's what it means.
Yep. Oxidation is losing, reduction is gaining. And then there's the famous
Leo the lion says grrr.
It's the one who likes?
You do.
MoNaCo likes.
I
Because
like
the word electron is in it.
Oh, yeah, I like them both because I'm easy to memorize. But anyways, losing electrons is oxidation.
And gaining electrons is reduction.
Good. That's the basics. Let's move on.
There we go.
Let's
Just
take off
a way
the
to remember
training
it, man.
wheels.
Just a way to remember it.
Okay. So if there's a reduction, there's got to be an oxidation because the law of thermodynamics, the 0th law of thermodynamics, says that all mass and matter and energy must be conserved. So if you lose electrons, something's got to pick them up.
And so then again, if there's an oxidation, there must be a reduction.
We say that these are equal and opposite or mutual and simultaneous.
Right. I mean, think about it. If somebody's going to lose an electron,
somebody else has got to pick it up.
Right. And if somebody picked up electron, somebody must have lost it.
So that goes back to the conservation of charge.
Right, and we could actually rebalance equations based on charge now and not just mass.
And that's pretty much what we're going for. But let's get some of these basic rules down for assigning oxidation to numbers to elements within compounds. And this is what we're doing in our first POGL of the unit.
Right.
But the pure elements aren't covered in that POGL.
Well, guess what? They're always 0.
Right, so a pure element, meaning found in its elemental form, like a big old chunk of gold sitting on the table is pure. We say that has an oxidation state of 0.
Because it has the same number of electrons as it does protons. That charge is neutral.
And it's not going to react with anything. We say its potential, its redox potential is 0. It doesn't have a plus, it doesn't have a minus, it's not reactive.
Don't want to do nothing.
Pure, it's not going to do nothing.
Now remember, ions are not pure elements. They have already gained or lost an electron, so that changes them up just a little.
Which is why in stable ionic compounds, we uncrisscross the oxidation state charges from our subscript. So we kind of like bring them back up. And you'll see this when we do some practice.
Yep. And the key here is that the overall, stable means the overall compound has a charge of 0.
Right.
So when we add up all those oxidation states times how many of them there are, it's got to equal 0.
0. Otherwise, it's not a compound.
Now we can work backwards knowing that.
It would be an ion if it did not equal 0.
Right.
Which is where we're going to go eventually.
Here we come.
Covalent compounds is just the same as for the ionic compounds. So some of the oxidation numbers in the compound must equal 0.
Right. The thing that we want to maybe put as a little side note here, I think MoNaCo milks are looking for a little they didn't write this, but I did kind of thing, right? The covalents don't necessarily obey the first element is positive, second element is negative rule like the ionics did.
So pay real close attention to your POGL, to what hydrogen and oxygen do in a couple very rare scenarios in order to understand how that particular thing works out.
Right.
Biggest deal and easiest, in my personal opinion, is ions.
Sure. I mean, they have a charge right on them.
It tells you the oxidation state of the whole ion. So if your ion was -1 charge, the sum of the oxidation numbers of all the atoms and ions that made that must equal -1.
Right. And this is even just for, I have a plain ion. I have an Na+1 sitting there.
What's its oxidation state?
Well, it's +1.
It's +1. It's
right.
Whatever the charge on the ion is, including polyatomic ions.
Right. No, we will see here in a minute that that does work for polys also.
So, examples of assigning oxidation numbers to some elements. So for
Okay.
pure elements,
Okay. Let's find the pure elements in here first. I got my fingers crossed, smartboard. But whoa. That one's yellow. Put that one down.
put that down.
Yeah. Let's go blue or red. Or black.
Pink?
Blue or red. Blue or red.
Blue or red.
All right. So we're looking for just pure elements. Oh man.
Those are our pure elements, the aluminum and the sodium by themselves. They are pure because they are sitting by themselves. They are not in a compound. They are pure. So for ionic compounds, and I hope our calibration fixes itself a little bit, we'll look at the same.
All right, so let's identify our ionic compounds. Oh boy.
Those are our ionic compounds.
Okay. And notice I pulled up the elements from the periodic table.
Okay.
Okay, because I see that Na has a +1 charge.
Okay, so this would be like,
right? And then Cl has got to be a -1 because it's ionic. And look at our two charges, add up to 0. We're good. Okay. Now AlCl3, I see Al is a +3 because that's all it can be. And then Cl has got to be a -1 because ionics start with a positive and then a negative, and I happen to have 3 of them. So when I multiply that out, I get a +3 and a total -3 charge, giving me an overall neutral charge. I am a neutral ionic compound. Assigning those numbers is critical. That's what this whole unit is about, because we're going to find that those numbers are going to change from one side of the arrow to the other. Okay? Okay, covalent compounds. We have, let's do this slow. Because look at real quick, when I look at my periodic table, I have H, I have O, and H, I don't know if it's a +1 or a -1, right? But I do know that oxygen should be just a -2.
and you know that the sum of them all
should be 0.
0.
So when I have a -2, I need 2 of something that negates that -2, so it's got to be plus. And it just so happens I only have the 1 plus, so it's going to be +1. And we can do it algebraically.
which is what I just did.
Which is what we just did, which happens when we have multiple positive choices. In this case, we rationalized that it had to have been positive, and guess what? There's only one positive choice, so that does make that a wee bit easier. But when I end up with 2x = 2, I got to divide both sides by 2, and I get 1.
Oh, yep, 1, not 2. Ha-ha! Ha-ha! So,
Okay?
algebra,
and sometimes they're easier than that, and we don't need to do algebra. Okay? Sometimes they're, not. So simple and polyatomic ions.
that's a simple ion.
There you go.
It's a +2 charge.
It's what I see.
What's its oxidation state?
+2.
Moving on.
That was really that simple.
Yes.
So here's where it gets a little bit more complicated. Okay, so now the overall charge of this ion is -2. And now when I start looking, I see that sulfur has multiple states, but oxygen has 1. So let's start with what I know. I know oxygen has a -2 charge. I have 4 of them. gives me a total of a negative 8 charge. So I need a positive charge in such that I end with a total charge of negative 2. Here's some more algebra. Bro. Okay. So I get x equals 6. And look up at the periodic table. Lo and behold, 6 is a valid choice. Here we go.
Yay!
Yay! And that's how we do it.
And it all comes back to the idea that the sum of the oxidation states for a polyatomic ion is equal to the charge on that polyatomic ion. I set it equal to negative 2. That's why my algebra worked.
Correct. And for all stable compounds, we're setting it for 0. And now we just learned how real quick to assign oxidation numbers. We need some practice.
Yeah.
And now we can do it. You need to be able to identify these reduction reactions and oxidation reactions real quick.
The POGL's a great start. First POGL of the unit's a great start on that. And the practice pages, I had some students already doing practice pages after they did the POGL without even watching this video. So
that's what I'm talking
awesome.
about.
Thanks, everybody.
And hey, wait. If you haven't done the practice pages yet and now you watch the video, go ahead. You don't need to wait.
Yeah, for sure.
Use what we learned in the video.
Thanks, everybody.